Hi, this is Dr. G. Vikas Paul. In this session, we'll discuss about the continuous beam. What is a continuous beam? A beam which has more than two supports is known as continuous beam, or we can say a beam which has more than one span. You can see the figures here. There are three supports, simple supports, span L1, L2 in one figure, and in the second figure it is fixed beam, fixed continuous beam. Intermediate support is there and fixed end supports are there. In continuous beams, the intermediate support restrains rotation. Therefore, moment will be taken place at intermediate support. This is very important point if we have to remember in the continuous beam. At intermediate support in the continuous beam, at intermediate support, moment will be there. Moment is not equal to 0. Moment is present. We need to find out the moment. So here if we see in the first figure, simply supported continuous beam, total number of reactions is 4. How? At A it is 1, at B it is 2 reactions, vertical and moment. At C it is again 1 vertical reaction, total 4. 4 minus 3 is 1. So it is indeterminate structure. Continuous beam it is an indeterminate structure because the ds value is not equal to 0. So if we see the other figure, fixed and continuous beam, fixed beam with continuous support. So it is here it is at one end it is 3 reactions, at other end 3 reactions, and at the center 2 reactions, one vertical and one moment. Therefore here also, here it is 3 plus 3 6 7 8, 8 minus 3 5. So again it is an indeterminate structure. The other points we have to remember is when continuous beam is simply supported, that is in the first figure, moment is equal to 0 at the ends. That means at A and at C, M is 0, M is 0, MC is 0, but MB is not equal to 0. B is intermediate support. When the beam is fixed, the moments will not be equal to 0 at supports. If you see the second case at fixed, in which we have fixed supports, okay, with intermediate support, there MA is not equal to 0, MB is not equal to 0, MC is not equal to 0. We need to find MA, MB, MC, right? So analyze the continuous beam means here we need to find MA, MB and MC. Next point is, due to continuity of beam, midsection of beam is subjected to sagging moment and the supports are subjected to hogging moment. So if you see the deflection curve when there is UDL on this continuous beam with fixed ends, so at A, at support, it is hogging, and at between A and B it is sagging, and at B, at intermediate support at B, it is hogging, negative bending moment, and between B and C it is sagging plus positive bending moment. At C, at support C, it is hogging, negative bending moment. So MA, MB, MC we need to find. Now let us discuss an important theorem, Clapeyron theorem, or it is also called as 3 moments theorem for continuous beam. So coming to the statement, sum of all moments at A, B and C is equal to sum of the areas and centroids of corresponding 3 bending moment diagram. So if we consider a continuous beam as shown in the figure with fixed end supports at A and C and intermediate support at B, and UDL is there, W1 is load on AB and W2 is a UDL on BC, I1 is a moment of inertia for AB and I2 is the moment of inertia of C. Similarly, L1, L2 are the lengths. So consider the continuous beam fixed at A and C and the intermediate support at B. Now if you see this deflection curve here, you can see the deflection curve, and theta BA is shown here. You can see at B, to the left side theta BA, to the right side theta BC. So theta BA is equal to minus theta BC. So according to this theorem, MAL1 plus 2MB into L1 plus L2 plus MCL2 is equal to minus x into A1x1 bar by L1 plus A2x2 bar by L2. This we need to prove now. Okay. Now A1 is the area of bending moment diagram for first load considering simply supported beam. So you can see the bending moment diagram considering simply supported beam here. A1, A2 are the areas, x1 bar, x2 bar are the centroid, the distance of center of gravity from A. So to derive the relation between MA, MB and MC, let us draw a tangent line. Okay, so for this, before that let us draw the bending moment diagram for fixed end supports. So you can see the moment here. At A it is MA minus MA, at C it is minus MC, at B it is minus MB, at B it is minus MB. As it is center, deflection will be more. So we have shown in this way. Why minus here? Because we know that at supports and intermediate supports and that's end supports, there is negative bending moment, hogging, therefore minus. Okay, now see the deflection curve here. Now we have drawn a tangent at B, and we have extended it. It is TAB is a deflection and TBC is a deflection. Now if you see the figure, theta BA is equal to TAB by L1, theta BC equal to TBC by L2. So if we find TAB, TBC, then we can solve the TB and TBC. Okay, now so TBA equal to minus TBC, it is a compatibility equation. So TBA equal to TAB by L1, TBC equal to TBC by L2. So TAB and TBC are the vertical distance of ABC at a tangent B. So from moment area method is more second theorem. Area of, so deflection is nothing but TAB is nothing but area of M by A diagram into center of gravity distance x bar. So TAB equal to area of M by A diagram of A and B into x1 bar. So here you can see the combined bending moment diagram for simply supported case and fixed end moment. So A1, A2 areas, x1 bar, x2 bar, you can see the figure. So TAB equal to area of M by A diagram of A and B into x1 bar. Now TAB equal to, what is the area? So 1 by E I1 into, so 1 by E I1 means M by A, no. So 1 by E I1, because for between A and B it is I1 into AX bar. So AX1 bar is the area into center of gravity for simply supported case above the line, you can see. Okay, plus, and below the bottom part we have divided into two parts, 1 and 2. So the first part area is half into L1 into MA, then x bar from A is L1 by 3, plus the second one area is half into L1 into MB. The centroid distance from A is 2L1 by 3. So TCB also similarly we can calculate. So 1 by E I2 is the moment of inertia for the between EC BC. So A2 x2 bar is for the top, and for the bottom we have divided again two parts, half into L2 into MC into L2 by 3 from B here centroid distance, plus half into L2 into MB into 2L2 by 3. You can see the figure clearly. So theta B equal to TAB by L1, theta BC equal to TBC by L2, theta BA equal to minus theta BC. So if we equate this one, theta BA equal to minus theta BC, so we got theta BA and theta BC values. Let us equate. So divided by L1, so TAB divided by L1, TBC divided by L2. So if we simplify it, we'll get finally MA L1 by I1 plus 2MB into L1 plus L2 by I2 plus MC L2 by 6I2 equal to minus 6 into A1 x1 bar plus I1 L1 plus A2 x2 bar by I2 L2. This is the case when I1 is not equal to I2. Okay. When I1 equal to I2, MA L1 plus 2MB into L1 plus L2 into plus MC into L2 equal to minus 6 into A1 x1 bar by L1 plus A2 x2 bar by L1. This is the 3 moment theorem or Clapeyron's theorem. So this is a proof. Let us see the steps for solving continuous beam now. So before steps, let us see applications. So continuous beams with both ends simply supported. For this we can apply 3 moment theorem. Both ends simply supported. Continuous beam with fixed end supports. So with fixed end support, both ends fixed end support. Continuous beam with the end span overhanging. For overhanging also we can apply 3 moment theorem as shown in the figure. So for this type of beams we can apply 3 moment theorem. Continuous beam with sinking supports also we can apply 3 moment theorem. Now steps, coming to steps. First step is draw the bending moment diagram for the given beam considering the beam as simply supported beam. Next, calculate area and centroid for the free body bending moment diagram, that is with for simply supported case calculate area and x bar. Now apply 3 moment theorem. Okay, find reaction at the support, draw SFD and BMD. Okay. So in the step second step here, it is area and centroid of total bending moment diagram, not for simply supported case, total bending moment diagram for simply supported case and fixed end supports bending moment, combined bending moment diagram. Okay, thank you.